Thanks for having me here this morning and on this particular topic, the microbiome and health and disease. And since it's a small group, I wanted to make it available all to you to feel free to ask questions and so forth. You don't have to hold it to the end. But this is a concept in terms of the microbiome that has captured the public's attention. And so I wanted to provide you some of the developments that have occurred over the last 15 years. I gave you a framework or sort of plausible biological framework so you can see how it can cross a number of different specialties in medicine. So just to introduce the concept of the microbiome, it's the microorganisms that exist within the GI tract, and it's not so much the bacteria that exists, but it's actually a whole collection of bacteria, the virome, the fungum, that is to say fungus and viruses as well as bacteria. However, most of the information we have available is related to the bacterial species and numbers and so forth. Just to reintroduce you to the GI tract, stomach, as we go through the small intestine to the large intestine, there's a pH gradient. In the stomach, the pH is 1. As you approach the large intestine, the pH rises to 7. And there's a corresponding increase in the numbers of microorganisms that exist per cc, such that in the stomach, relatively sterile, about 100 microorganisms per cc. And by the time we get to the colon, it's close to 1 trillion microorganisms per cc. Now, these numbers are astronomical, and that's what's for years and years made it difficult to understand and get a better grasp on the microbiome. But the relative difference is depicted here. In the microbiome, there's 10 trillion cells encoding 2.3 million genes, and that contrasts the human body, depicted by Earth here, which has about a trillion cells and encodes for about 20,000 genes. So there's a vast disparity in terms of numbers, astronomical, if you will. But what we've realized is rather than just having a large number of microorganisms, up to 5,000 different species, and that number increases as a result of some of the advances in molecular biology, no longer requiring culturing of microorganisms. But what we're learning is this microbiome does a number of essential functions, so many functions that it's been regarded now as an organ, an essential organ. One of the principal ones is pathogen protection, that is to say protecting the host, but it's critical as far as immune development in the younger years and continues to guide the immune system throughout our lifetime. And this is one area that's neglected, particularly in this time of talking about immunity and so forth. 80–90% of the resources of the immune system are directed toward the GI tract. And there's a close interaction in terms of that immune surveillance that occurs in the GI tract and the rest of the body, and we'll come back to that. Digestion, caloric salvage, about 15% of your calories come from fermentation material that was not absorbed or could not be absorbed in the small intestine. A number of different vitamins that you cannot retrieve in your diet or manufacture, such as vitamin K. Gut development is essential. Energy balance in terms of metabolism is critical. And drug metabolism, increasingly we realize a number of the medications we take are actually prodrugs that have to be metabolized into an active metabolite before they can be functional and absorbed in the GI tract. So a number of different functions. And so I want you to view the microbiome as an organ, but more than that, actually an ecosystem, where you have a number of different species working together in collection and concert with the host to create a stable ecosystem. And this ecosystem is depicted here in this photomicrograph. And it's useful to pause for a moment and look in the upper right here is the gut lumen. But the gut lumen, you don't have a large number of bacteria immediately adjacent to the epithelium. Rather, instead, you have a mucus layer that's produced by the goblet cells, and you can recognize the goblet cells in the epithelium there. And then beneath the mucus layer, there's an unstirred water layer, and then finally the gut epithelium itself. And the epithelium itself is the cells basically are shoulder to shoulder with a tight junction. So it regulates flow across this epithelial surface into the mucosa. And this is a schematic depiction. And in the schematic depiction, you see in the upper portion the gut lumen, the bacteria, the microbiome. But the microbiome is describing to you as an ecosystem. It does things, it produces things, and among them are short-chain fatty acids that occur as a result of fermentation of material. And these short-chain fatty acids, you learned them from organic chemistry, butyric acid, propionic acid, acetate, and that's the favored nutrition of the gut epithelium. But not only acting as a nutritional source, those short-chain fatty acids migrate across the epithelial surface and interact with the immune cells that exist in the submucosa. Now, you'll see this in a number of different areas here, and I don't have my pointer here, but in the lower center here, we have innate lymphoid cells that produce IL-22 and interleukin that stimulates goblet cells to produce mucin, but also these ILC cells produce IL-22 that stimulates antimicrobial peptides that are secreted at the luminal surface. Furthermore, ingress of bacteria as well as proteins that you can see here stimulate plasma cells that produce IgA, and then that's secreted in the luminal surface as well. And on the far right, you have these T cells, T helper, T regulatory cells, that are instrumental in terms of a pro-inflammatory state. When there's more bacteria and protein coming across the epithelial surface, we have more inflammatory cells that are stimulated, and then regulatory cells that are anti-inflammatory that produce cytokines that modulate inflammation. Now, I'm showing this as a static image, and it's not really an accurate representation. None of these immune cells linger in the GI tract. They are stimulated in the GI tract, and then they go back into the circulation and circulate across the entire body. So, as I said, 80–90% of the resources are directed toward the GI tract, but the components of the immune system circulate throughout the entire body, and the cytokines that are produced by the immune cells also circulate through the entire body. And we'll come back to that to see how it may affect other organ systems as a consequence of that. But that's an important concept, and the mechanisms of how that can occur has been worked out in the last 10 years, but that's another lecture. So an ecosystems can change. You know, after a forest fire, ecosystem is decimated, and it takes decades, a century, for a forest to come back in its original form. And rather than just focusing in on the plants, there's a whole ecosystem that's supported there in terms of plants and insects and animals, as well as the things in the ground as well. But the whole ecosystem is diminished, far fewer species there than before.